In this video, we're going to complete the KutaSoftware Infinite PreAlgebra free worksheet, Scatter Plots. I'll leave a link in the description below so you know how to access this free worksheet. Now, for our first page, it says to state if there appears to be a positive correlation, a negative correlation, or no correlation. Now, quickly going over what a positive correlation is, think about as we move to the right on our scatter plot, if our data points appear to be going up or getting higher, that's a positive correlation. As we move to the right, if those points appear to be getting lower in value, that's a negative correlation. And no correlation would be if, as we go to the right across our scatter plot, there's not a positive trend, so the points don't seem to increase overall, and they also don't seem to decrease overall. They're just kind of scattered around. So the next set of our directions is that when there is a correlation, we need to identify that relationship as linear or nonlinear. Linear, think of a line. Nonlinear, think of a curve. So let's go ahead and jump in to number 1. So in number 1, think about as we move to the right, what is happening with our points? So we're starting out fairly low, not a lot of change, but then all of a sudden, as we continue to go to the right, what's happening to those values? Those y values are getting larger. So because as we move to the right, those values are increasing, this is a positive correlation. Now we know it's a positive correlation, and since it is a correlation, we need to now identify whether it's linear or nonlinear. So as we move to the right, do those points appear to form a line? No, it is more of a curve. If you were to trace the points, you can see that it's similar to a curve. Therefore, this positive correlation is nonlinear. Let's move on to number 2. For number 2, as we move to the right, what exactly happens with the points? Well, we start kind of in the middle here, then we jump down, then up, then up, then up. So it's kind of seeming like a positive correlation, but then all of a sudden we drop back down, and then we go back up again, and then down, and then up. So because there's not a trend among the points, we're going to say that in this case in number 2, there's no correlation. Let's move on to number 3. In number 3, what happens with our points? As we go to the right, we're about the same here, and then we increase, we continue to increase, and then we continue to get higher until we're about up here. So overall, since as we move to the right, there's a trend of our points getting higher in value, that means that this is indeed a positive correlation. Now, also looking at this, because it's a correlation, we need to decide whether it's linear or nonlinear. And unlike number 1, where we had that very distinct curve, this one I would probably actually say is linear. As we move to the right, if we were to try to draw a line of best fit or a line that fit these points the best, it would probably look something like this. Whereas if we were to try to do a nice smooth curve, it gets a little tricky trying to follow those points exactly. So I think a line would actually be appropriate for number 3. So I'm going to say that it's not only just a positive correlation, but that relationship is a linear one. And again, let's scroll back up to number 1 to compare. In number 1, if we tried to draw a line that fit these points, the line would maybe look something like this, which doesn't really capture the overall trend or the overall way the points are growing. A nonlinear would work much better in the case of number 1. Whereas in, again, scrolling back down to number 3, the one we're currently working on, a linear relationship defines these points very well. Let's move on to number 4. And number 4, as we move to the right, what's happening to our points? So we start here. Then we need to decrease our value to get to these points, decrease again, and continue to decrease. So because overall the points are mostly decreasing, that means that this is a negative correlation. As we move to the right, our values are trending down. And like in number 3, if we were trying to draw a line or a curve that best fit the points, it would probably look something like a straight line. Therefore, I would say that this negative correlation, the relationship is a linear one. A line fits these data points fairly well. Let's move on to number 5. In number 5, what's happening to the values of our points as we move to the right? Well, starting with our first point, to get to the next point we have to decrease, then we have to decrease again, and again, and we're still decreasing all the way as we move to the right. So because the values are getting smaller, this is a negative correlation. And what would we say is the relationship of this correlation? Is it linear or is it nonlinear? Well, if we were to try to draw a line that best fit all of these points, it might look something a little like this. However, if we were to draw a nonlinear curve, it would look something like that. So I would say that the relationship in number 5 is indeed nonlinear. A nonlinear curve fits this a lot better than a line. Now onto our last problem for this set of directions, number 6. In number 6, as we move to the right, what's happening with the points? Well, you can see here we have 3 points at the value of 2 that are kind of spread on our y-axis. Then we move a little bit further, and again we have spread points. Continue to moving this way, the points seem to have both high values and low values, so there's really not a trend. So in number 6, I would say that we have no correlation. As we move to the right, there's not a trend down in values, and there's not a trend up in values. Moving on to the second page, for numbers 7 and 8, we're going to be constructing a scatter plot. So constructing a scatter plot is simply plotting the points of the given data. So if we're starting with 300 in the x and 1 on the y, we're going to capture that on the plot directly below the tables. So I'm going to zoom in just a little bit more. So in number 7, our first point is 300 in the x and 1 in the y. So this is our x-axis here, and this is our y-axis here. So we need to find 300 in the x, which, looking at our intervals, we're counting each line by thousands. So this is 1,000 here, 2,000, 3,000, 4,000, and so on. And we know that 300 is a little less than halfway between 1,000 and 0. So I'm going to put 300 in the x at approximately here. And then we need a value of 1 in the y. So if we're right here for 300 in the x, a value of 1 would put us here. There's our first point. And I'll put a check to signify that we've plotted it. Now we're going to do 801. So if I need 800 in the x, which is still less than 1,000, but a little more than halfway, and we have that same y value of 1, that point's going to go approximately here. Let's put a check. Now we're at 1,102. So 1,000 again is this line here. So 1,100 goes a little bit past that line, and we need to plot a value of 2. So 1,102 would be right here. Now we need 1,602, and also I'll plot 1,702 while I'm at it because they have the same y value, but different x values that are fairly close. So 1,500 would be approximately here, but I need 1,600, which falls here, and 1,700, which falls here, both at that value of 2. Next, now that I've plotted those, I need 1,803. So 1,800 falls approximately here, and moving up to that value of 3, we've got it here. And then 3,403 again. So let's find our 3,000 tick mark, which would be here. 3,400 would fall a little less than halfway between 3,000 and 4,000, so somewhere around here, and we need the y value to be 3. So moving up to 3, 3,400, comma 3. Now we have 4,700, so going past our 4,000 tick mark, but before our 5,000 tick mark, we need to go up to 4. So approximately here. And then 6,004. Luckily enough for us, 6,000 is indeed a line, so we just have to go up to 4 and find that intersection. And then lastly, 8,506. So 8,500 goes a little past 8,000, and we need to go up to 6. So right here. Now I know it doesn't ask us to do this, but let's think about the correlation. As we move to the right, what's happening with our points? The values are overall increasing, and we can even see that with our values. We're starting at 1 in the y, then we go to 2, then 3, then 4, and then we jump up to 6. So those values are increasing, and this looks like a linear relationship. So I would say it's a positive correlation that's linear. Let's move on to number 8. In number 8, we're dealing with decimals, but the same concept applies. We're going to plot each of these data points on our plot below, where this is the x-axis and this is the y-axis. So starting with 0.1 and 7.5, our increments are by the tenths. So this line here represents 0.1, and we're going to go up to 7.5, which is approximately here, between the 7 and 8. Now we have 0.1 and 7.6. So a point that's very similar to the point we just put, but a little bit higher. So right here. Now we have 0.3 and 4.5. So we're going to go to 0.3, which is this line here, and up to 4.5. Halfway between the 4 and 5. Now we're going to go 0.4 and 3.2. So finding 0.4 in the x and then moving 3.2 up. So a little less than halfway in between to approximately here. Now we have 0.4 and 3.3. So very similar to the point we just plotted, just a tad bit higher. 0.4, 3.3. Now 0.6, 1.4. So going over to 0.6 and up to approximately 1.4. A little less than halfway between 1 and 2. Then we have 0.6, 1.7. So a little higher than that, a little more than halfway between 1 and 2 in the y. We'll have our 1.7. So 0.6, 1.7. Ooh, and then we also have 0.6 and 1.8, so just a tad bit above that point we just plotted. Then we have 0.9, 1.5. So going over to 0.9, which is this line here, and up to 1.5. And then lastly, 1 and 1.7. So here is our line for 1, and 1.7 falls approximately here. Now again, it doesn't ask this, but overall, I would say these points are trending down. Even though towards the bottom, they start to go back up again, overall, the majority of those points are decreasing as our values are increasing. So I would say this is a negative correlation, and I would also say that it's a non-linear negative correlation because a curve fits those points very nicely. Let's move on to our next set of directions. Our next set of directions state to construct a scatter plot, which we did in 7 and 8, but now we're going to find the slope-intercept form of the equation of the line that best fits the data. So we've already constructed a scatter plot, like I stated, up in 7 and 8, so we know how to do that. But this next part's a little bit trickier. We're going to find the slope-intercept form. Remember, that's y equals mx plus b of the equation of the line that best fits the data. So after we plot, we're going to estimate a line that fits the data best. So we're going to have a linear relationship, which means that these data points will most likely have some form of correlation, whether that's positive or negative. But first, let's start by making the scatter plot. So since we've done this previously, I'll go through a little more quickly. So we have 10, 700, where this is my x-axis and this is my y-axis. Make sure to label so that you know which axis deals with which values. So 10, 700 would be here. Then we do 10, 800, which is here. 3,400, which falls here. 3,500, which falls here. 4,300, going to 40, then 300. 6,200. 7,100. 7,100 again. So these 2 points fall right on top of each other. So I'm just going to draw the again. Although it's hard to see that there's differences there, but remember there's 2 different data points right there. 8,100. And then 100, 200. Now, if I were to draw a line that best fit this data, well, doing it without using any technology, I would take a straight edge and try my best to get the line as close to all the points as I can. You want to draw a line that tries its best to capture or get close to all the points. But remember, it's a straight line, so you're not going to necessarily even touch any of the points, but you're trying to get as close to all of the points as you can. So I'm going to start here and draw my line down. Something like that. That seems to capture the points fairly well. I have a few that are above the line, and this one actually looks like it hits the line, and so does this one, and then a few below the line. And what I'm going to do to make my line in slope-intercept form is calculate it using the 2 points that hit my line. So this point here and this point here both hit the line. So that was 10, 700, and it was 3,500. Slope-intercept form, y equals mx plus b. I'm going to start by finding my slope, which is the change in y over the change in x. So my slope m is going to equal change in y, so I'll do 700 minus 500 over 10 minus 30. And remember to subtract the points the same way. So I used this first and subtracted 500. So I used the 10 first and subtracted 30. This is going to equal 700 minus 500 is 200 over 10 minus 30 is a negative 20. So when I do out this math, 200 divided by negative 20, that's approximately negative 10. So I have a slope of negative 10. So y equals negative 10 times x plus, what's my b? What's my y-intercept? You can see where I crossed that axis was at this point here, 800. So negative 10x plus 800. And we can confirm that is indeed our y-intercept by plugging in either of these points and seeing if we get the same value. So plugging in 10 for x, we'll get negative 100 plus 800, which does indeed equal 700. So because this point right here checks out, we know that 800 is, even though I just estimated with how my line was drawn. So I would say that this is slope-intercept form of my line of best fit. It's a negative correlation that's linear with this as the slope-intercept form of the line of best fit. Now the other and more accurate way to do this is to use technology. So let's jump over to Excel. So here I am in a blank Excel file. I'm going to write my X column and my Y column. These are my 2 different values. Now for X, our first data point was 10, 700. So essentially I'm just going to copy the table from my worksheet. So the next was 10, 800, then 3,400, then 3,500, and so on. I'll continue typing. Feel free to do the same on a computer or just follow along. Now, once I have those typed in, Excel allows me to easily plot these points in a scatter plot. What I'm going to do is just click and drag and highlight all of these points. And then once I highlight all of those points, I'm going to go to Insert, and I'm going to go over and choose a chart. And I want a simple scatter plot, so I'm going to select that option here. And here is my scatter plot. I'll resize so it fits in this window. And it looks similar to the one we just drew, just with a slightly different scale, which is okay. Now Excel lets us find the line of best fit, that linear slope-intercept form equation, very easily. All we have to do is either go over to the plus button on our chart or go over to Add Chart Element, click, and then we're going to go down to Trend Line, and we want that linear trend line for the line of best fit. And there we have it. There we go. It automatically finds that line of best fit. But what we need is the equation. How do we see that? How do we find this equation? It's plotted it for us, but we want the equation. So hover over it, double click, and then you'll see Format Trend Line, and you'll go down, down, down until you see Display Equation on Chart, and when you click that checkbox, the equation will pop up on your chart. So I'm going to move this up a little bit higher so we can see. Here is our true equation for our line of best fit. The mathematically correct one, that's not estimated. Negative 7.381 times x plus 709.05. This is the correct equation for the line of best fit. However, what we did on our worksheet, we drew it out by hand, so it's going to be slightly different since we were estimating. And again, one more time, if you were stuck with trying to display that equation, hover over the trend line, double click, and it will pop up the Format Trend Line, and all you have to make sure is that you display the equation on chart. Make sure that checkbox is indeed checked. So you can see here, we had a negative correlation, and that's easy to see because the slope is negative. Not only can we see it visually, but the slope tells us whether it's positive or negative. Now, let's move on to our very last problem on this worksheet. And if you've been finding this video helpful, don't forget to click that thumbs up button. But for now, let's continue on, and I'll erase some of this work so that we have some more space. Again, we're going to start by simply plotting each of the points. This is our x-axis here and our y-axis here. So 120, we're going to find 1 and then plot 20. 240, find 2, plot 40. 350, find 3, plot 50. 460 would be here. 570. 780. And then we have another 780, so there's actually 2 points here. 980 falls here, and then 1080 here. Now, if we're doing a linear line of best fit, that's going to be a straight line. So again, I'm going to attempt to capture that just by eyeballing it and trying to draw a line that closely captures all of the points. So I'll start here and draw something maybe a little like this. So you can see we have a few points above the line and a few points below the line, and in my case, none of the points are touching the line. So I would have to estimate 2 separate points from that line. So right here looks like a good intersection point on my grid line, and here looks like another good intersection point on my grid line. So I would use those 2 points to 35, and it looks like 775. I would use those 2 points I just created to find my slope-intercept form. Again, finding the change in y over the change in x to get the slope, and then using one of those point values, either 775 and 235, to solve for my y-intercept. However, as opposed to doing that, to get a more accurate representation, I'm going to go ahead and go back to my Excel worksheet and use technology to help. So jumping back over to Excel, I'm going to scroll down and make a new plot. Here's my X values and my Y values. So filling in those X values first. One, 2, 3, 4, 5, 6, 7, 7, 9, and 10 were the X values, and the Y values that went with those associated X values were 20, 40, 50, 60, 70, 80, 80, 80, 80, 80. Again, I just took these values from the table and entered them into my Excel spreadsheet. Now, just like before, we're going to highlight all of these points, go to Insert, and we're going to select a scatter plot. I'm going to shrink it so that it fits a little bit better in our window, but there we have it, our chart of X, Y values. But what do we need? We need the slope-intercept form of the equation of the line that best fits the data, the line of best fit. So we're going to, under our chart design or our chart itself, we're going to add a chart element, or you could do so by clicking the plus button over here, and we're going to select trend line, and we want a linear trend line. We want to see that equation, so we're going to double click our trend line and display the equation on the chart. And there we have it, 6.4286 times X plus 29.286. This is our line of best fit, which you can see that slope is positive, which means it's a positive correlation. Let's go back and write this equation on our worksheet. So again, this equation was y equals 6.4286x plus 29.286. That was our line of best fit when we used technology. See how that equation compares to the one that I've drawn here. I know one thing's for certain, that both the slopes are definitely going to indeed be positive, because as I move to the right in my scatter plot, my values for my y increase overall. A positive slope, a positive correlation. And with that, we wrap up this scatter plot worksheet. If you have any questions, please feel free to leave them in the comments below, and I or one of your peers will get back to you as soon as we can. But as always, don't forget to like, subscribe, and share. Happy learning!